All right, we're going to go ahead and get started. So this doesn't apply to you guys who are in attendance right now, but I'm sure you all got the email about the 9-10 a.m. recitation, how Dr. Zalecki had to teach that for me. I had a family emergency, and so I am not in Michigan. But what does apply to you guys today is that my recitation notes are going to be a little bit on the sloppier side. I just wanted to apologize for that ahead of time, just because this week has been a little bit hectic. But today we are going to be looking at the MBT and critical points. I believe that has been presented to you already in lecture. Okay, take one last look. I am just going to dive in, start sharing my screen. Okay, so we're going to be looking at sections 3.1 and 3.2 today. We'll do a little bit of graphing, but this is some pretty basic graphing relative to what we will be looking at going forward. It's more so just like conceptually, we're going to represent what these maxes and mins look like and how to kind of break them down. These first two problems are going to be really simple, really straightforward. So we are asked to sketch the graph of the function that is continuous on closed bracket 1 to 5 with the given properties. And that closed bracket will become important when we talk about the MVT later, but I'll remind you guys that that means that 1 and 5 are included. So we're given two absolute extrema, max and min. You'll also see in my note, and you'll hear me refer to the absolute max and min as global max and min, or extrema. And then we're given a local, and then a local maximum and two local minima. So I just wanted to point out that we have two written under local minima. It's a local minimum, and it is also our absolute minimum, our global minimum. And technically, all absolute or global extrema can be considered a local minima. So don't get tripped up by that. This is going to be the same point. We're not going to write two max or two mins at the point x equals 2. Basically, you can disregard that it is a local minima at 2 because relative to the entire function, we're more concerned with the fact that it's an absolute minimum. So here I've got an alternative graph, but I'm going to go through plotting these out with you guys if you were to do it on your own. So starting with our absolute max, we don't care what the function value is, just relative to the rest of the function values, we want it to be the greatest. Our absolute min is going to be at 2, so I'm going to put that all the way down at the bottom of the graph. Then we've got a local max at 3. So we'll put that, say, here. And then a local min at 2. And what I'm doing as I'm drawing these points, oh, and at 4. I meant to say at 4. So what I'm doing as I'm drawing these points and visualizing them relatively is I recognize that if I'm going to go from having a minimum here and then having a maximum and then a minimum again, I need to be able to, these points need to line up in such a way that I can draw them to connect them. And so I've got this max relative to this min here. And when I draw it, it'll look something like that. And my graph has gone off of the axis a little bit, but that's okay. This is just representative. So we've got a global max at 5. A global max has the largest function value on the entire function for the given interval. Obviously, so the arrows in this case don't necessarily apply because we're given the range of 1 to 5. So we only really care about the function and what it's equal to between 1 and 5. But we know that this here is going to be a max. So we'll say that it looks like this. Even though we visualize functions with having those arrows to suggest that they are going on to infinity, but within the context of this problem, it's inclusive of 1 to 5, so we don't have arrows. So again, we've got the function value that is the least on the interval 1 to 5, even though, say, if we were to visualize this function going down to infinity, technically this wouldn't be the least function value or the function value with the lowest value. But again, within the context or within the range 1 to 5, this is what our graph would look like. I also threw up another example here. Just because all the so our maxes don't have to be above the x-axis or below. I think that this is pretty obvious, but sometimes it can trip students up not to have seen an example like this. Again, this is all relative. We really only care when we're given, especially when we're given such little information, and all we're told is whether or not it's a max, a min, a local, or a global. We just care about the relative function value, which is why I haven't even assigned any function values to this axis on the left. I don't expect there to be many questions on this one, but feel free to ask at this point if you do have any before we move on to the next one.
Isn't relative just like, or like the local max, isn't that like another word for relative?
Exactly. Mm-hmm.
Okay, thank you.
Yep. All right, absolute max at 3. Or number 9, we have an absolute max at 3, absolute min at 4, and a local max at 2. So this is going to be R3. I'm only going to mark that one just for the sake of time. So we'll say our absolute max is up here. Our absolute min is down here. And then we've got another local max at 2. So in order to have, so this part here should be simple enough to connect. That's going to be a max. That's going to be a min. We're told that the function is defined between 1 and 5. So we'll say that it comes up to here. We'll say it comes up to the x-axis, and that this concludes what we know about the function. We can't go any further. What we're going to have to do in order to make this here a maximum is we're going to have to do some squiggling. So we'll bring it down here. Oops. Let's do it like that. Something like that. Local max at 2. Yep. So this is how I would do this problem. I'm going to make a note to myself just to make sure that I didn't miswrite this as maybe it should have been a minimum. I don't think that I miswrote it, but I will take another look. And when I send you guys out the recitation note, if there is a min, I will put it in a different color. If this is supposed to be a local minimum, I'll put it in a different color so you guys can take a second look at that. But if you were given a problem like this and you have 2 maxes that are basically adjacent, you're going to have to put a min in there at some point in order for there to be a change in concavity and inflection in order for you guys to have that max. And then, so basically, if you're going to have a maximum, you can't just lump it on to the next maximum. Otherwise, that would be 1 maximum. All right. So that's really all we're going to do. I think we might do beyond the little graphs that I throw in here for representative purposes. That's all the graphing that we're going to do for today. We will do more graphing probably next week and the week following, I would guess. But this is all that you need to understand for today, is just relatively, conceptually, what is a maximum and a minimum, so our extrema, and then global and relative or local. So there's global and absolute. Those are the two, those two terms mean the same thing. So a global maximum or an absolute maximum. And then there's local or, what was the other word that I used? It's escaping me. I said it just a minute ago, but I will say it again. So we're going to find the critical numbers now. So what is a critical number? What is a critical point? We will use critical points to do things like candidates tests, and we will use them in those big bad graphing problems that I keep alluding to, where we graph a really complicated polynomial that maybe has asymptotes and holes and things like that. And critical numbers are important because that's how you find where a max or a min is. A critical number is where the derivative is equal to 0. It's that x value at which the derivative is equal to 0. So within the context of this graph, x equal to 3 is a critical point because we have this derivative of 0. It's a maximum, and then minima are the exact same thing. It's a maximum, and so its derivative is going to be equal. And so the x value that corresponds to the derivative being equal to 0 is a critical point. You wouldn't necessarily be marked down for giving the answer in coordinate form, but sometimes we're finicky about it. This is a case where we're not. You could say that there's a critical point at x equals to 3, and that would be sufficient, so long as they don't ask you to specify whether or not it's a maximum or a minimum, or global or local. So for these two examples we're going to do here, it's just differentiation, setting it equal to 0, and maybe some algebra to figure out exactly what that x value is to isolate it. So when we take this derivative, the derivative of 4 is 0, derivative of 1/3 x is 1/3, and then when we drop that 2, we get negative 2/2, or just negative x. And so so simplifying this to negative 1x, I'm going to add x to both sides, and I get that x is equal to 1/3. So we're not going to do any graphical representations of this, but what you can take away from this is that there's either a maximum or a minimum at x is equal to 1/3 for this graph. And as far as this problem goes, that's all you need to answer and all you need to know. Next example is going to be, so 31 and 33 are just going to be more computational examples. So first we'll take our derivative, power rule, and then technically power rule, but we all know how to take the derivative of a linear function. And now, so we are going to set this equal to 0, but we're going to need, in order to figure out what these x values are, we're going to need to factor it. This, looking at this off the bat, you might think that we'd have to factor it, but after taking the derivative, you see that there's really only one x value, and it just becomes a manipulation on either side of the sign in order to consolidate those constants and figure out what the x value is. In this case, we have multiple x values, and we're going to have to factor it. And so how are we going to factor this? We're first going to take out the 6. Whenever you have the opportunity to take the constant off of this leading variable, it's going to make factoring way easier on you. And so we factor a 6 out of all these, and this is what we're going to end up factoring into our classic 2-term factors. And so we think, okay, what 2 numbers will multiply to give us -6, but then also add to give us -1? So what numbers multiply to give -6? That's 6 and 1, but there's no way to add or subtract those numbers such that the answer is -1. So then our other 2 options are 3 and 2. So if we were to multiply -3 and +2, we would get -6. Or if we were to add -3 and +2, we would get -1. And so now we can determine what our x values are. So 6 is negligible in this case. It's just a constant. There's no instant at which 6 is going to be equal to 0, because by the multiplicative property of, I forget what it's called, but basically all of these factors multiplied, they in isolation can be set equal to 0 to figure out what these x values are. Technically 6 is a factor in this case, but there's no x value that we can isolate. And so what we're looking at here is basically it's a phrase that says 6 is equal to 0, but that's never true. So we just throw this point out. And then we get that x is equal to -2 and x is equal to 3 for our 2 critical points. So again, those could be maxes or mins. Any questions so far? Okay. One more example. This one's a little bit different. So for these 2 examples, we were able to just crunch through them with the algebra skills that we have. For this one, it's going to be a little bit different, but something that we're all familiar with. So first we'll start off by taking the derivative, power rule. Then we factor out a t in this case. There's no constant that is common to these 3 terms, so we're just going to factor out a t. And then, so we've got 2 terms at this point. What we can take away from this t multiplied by this 4t squared plus 3t plus 2, since we can set each of these terms equal to 0, is that t equals 0 is going to be a critical point for us. So that's one of the answers that we can get right off the bat. But now we've got to think, okay, how do I factor this? Looking at these factors, it doesn't look easily factorable. And when I was doing this problem myself, I tried to factor it for a few minutes, and then I turned to the internet and I looked up a factor calculator, and it's not factorable by traditional means. So by that I mean we can't break it up into 2 factors and then isolate what x is equal to in both cases. And so what we do in that case is we use the quadratic formula. So this should be familiar. It's set equal to t in this case rather than x. It's negative b plus or minus the square root of b squared minus 4ac over 2a. So we'll plug in these factors. In this case, a is 4, b is 3, and c is 2. And then when we plug in these factors, the issue arises right here that we have this 3 squared term, which is going to be 9, and then 4 times 4 times 2, which is negative 32, which is greater than 9. And now we have a negative value underneath the radicand. And in order to simplify this, which it can be simplified further, but since we're trying to determine whether or not there are other critical points, I did not simplify it further, because what I can gather from the fact that there is a negative value underneath the radicand is that in order to simplify it, I would have to pull out I, the imaginary number I, the square root of -1. And then all of a sudden, I'm no longer dealing with rational numbers. I'm dealing with the imaginary number line. And we're not asking for zeros on the imaginary number line. We're talking about x values that pertain to polynomials, because this is a polynomial. We're not talking about irrational number sets. We're talking about rational number sets. And so we can't pull any zeros. We can't pull any critical points out of this term here. And so what we get from that is that this part here is negligible. And the only answer to this problem, the only critical point to this function g of t, is t equal to 0. Because we tried to factor this and then we couldn't. Because we then tried to use the quadratic formula, because that's our backup, that's the big guns. And then when we went about the quadratic formula, we got an irrational number. And so this can't be applied to a polynomial that exists within the rational plane. And so t equals 0 is our only answer. And then I threw up the graph over here just so that we could all kind of have a look at this, because if there's only one, say we've got a normal quadratic function, say that's x is equal to, or y is equal to x squared. My drawing, the pencil's a little bit on the thicker side, so you can't necessarily tell. I don't know if you can tell what I'm trying to represent here, but the difference is that we've got this long, wide increase here rather than this down and up. And I really only threw this up here because when I was doing this problem, I was like, okay, well, why would the function why would I not be able to come up with another critical point if the function is as complicated as it is, if it's t to the 4th? Because we know functions like these to be a little bit more on the squiggly side. And so I threw up this function here so you had sort of a visual representation of how this is similar to other functions that we've looked at, but a little bit different in that we have this wider and slower decrease and increase around the critical point, but still there is only one point on this function that is equal to 0. And this is our derivative function. Actually, I'll keep that. Okay. Any questions on this one? On the thought process that goes into it? All right. Now we are going to find absolute maxes and absolute minima, maxima and minima, excuse me. So the only difference between finding the critical numbers of the function and then finding the absolute maxima and minima. So there are two differences, I should say. So first, they're asking us to designate whether or not these extrema are max or min. So they want us to figure out whether it's going to be concave down. It's going to look like this, if it's going to be a maximum, or if it's going to be a minimum. And then we also have to figure out relative to the other max or mins, if there are any, whether or not they're the absolute or not. So we need to figure out if they're a max or a min, and then if they are the absolute or if they are local. This problem doesn't necessarily ask us to label each one as local, but we want to identify if there are multiple maxes or multiple mins, which one is going to be the absolute or the global. And so we're going to go about this just like we did with the last problem. First, we're going to take the derivative. This one's fairly simple. So we do the power rule in both cases, linear function, and then x squared, we drop the 2. And then we get that x is equal to 2. So this is our only critical point. So we don't have to think, okay, we don't have to compare two maxes or two mins in this case off the bat. The only thing that we have to do is identify whether or not this is a maximum or a minimum. So these two examples, 45 and 47, I show two ways to figure out whether or not something is a maximum or a minimum. And this way is one that might save you time. This way is the way that I recommend you do when you've got more complicated problems. You've got multiple extrema to compare, because it's a little bit easier to keep track of things. And you'll see what I mean when I get to the next one. But thinking about just this one particular point, we can determine whether or not it's a maximum or a minimum by first finding its function value and then finding the function values to the left and the right. So if the function values to the left and the right are less than the function value at this point x equals 2, then we're looking at something like this, and we're looking at a maximum. And then by the same logic, if the function values to the left and the right are greater, then we would be looking at a minimum. So first, we're going to assess by looking at function values. So first, f of 2, we get that that is 16. And then I chose f of 1 and f of 3 because those are easy numbers to work with. I get f of 1 equal to 15, which is less than 16. And before I even do f of 3, I'm going to guess that it's going to be less than 16 also, which it is. And so since we have two function values that are less, so we'll say that this here, oops, say this is 16. And then at 1 and 3, I guess I drew my scale a little bit off here, but this point here would correspond to 15, and this point here would correspond to 15. For the sake of this problem, this would be 1, this would be 2, this would be 3, but my axis is off. And so we can visualize that since this maximum is greater than the function values to the left and the right, that it's going to be, well, I just said it's going to be a maximum. Okay. And so there's an absolute maximum at x is equal to 2. So that was assessing my function values. Now we are going to assess using the first derivative, whether we're going to think about whether or not the function is increasing or whether or not it's decreasing, which will give us the same sort of visual, but it's different in terms of the symbolism that we're going to use. So going forward, we're going to use this method a lot more often, but I thought that this was kind of a good stepping stone to help conceptualize. And also, if you were given just this problem and asked to assert whether or not this value x equal to 2 is a max or a min, and you weren't told to use a number line, you weren't told to use a candidate's test, these are things that have not been introduced yet, by me at least, then you could do this and you would still get the right answer. But going forward, we will use this method that I'm going to use in 47 a lot more often. So we've got f of x is equal to this polynomial here, and we're given the closed interval -2 to 3. I didn't address the closed interval 0 to 5 before. For these two problems, it doesn't really come into play with how we're going to solve it. It will be much more important when we do MVT examples towards the end of recitation. But basically, so an example of where it is applicable, and this should be on the easier side to visualize, is say we were doing this for a trig function. So trig functions, they go on and on and on and on and on and on and on. So and technically there's a max and a min at all of these points, and it could go on until infinity. And so you have to specify maybe from -2 pi to 2 pi. The only time with a polynomial that you would really have to think about this range here, if you're simply just being asked to find the absolute max and the absolute min, is say if they threw in, say if there was a maximum that was outside of the range and they were telling you neglect it. That's what that would mean. Say that there was a maximum for this problem at x is equal to 4, then you would not take that into consideration of which one is the absolute max or the absolute min, because they're telling you, don't worry about the rest of the function. We only care about this range -2 to 3 with the values inclusive. So diving into this problem, we'll first take the derivative. Then we're going to factor out a 6. And now we'll factor this polynomial here. So what two numbers will multiply to get -2 and add to get -1? We get 6 times x minus 2 times x plus 1. Again, we don't really care about 6 in this case. I don't think I meant to erase that. Oh, I guess I didn't write anything down about 6. We don't care about 6 in this case. The only two critical points that we care about, the only two critical points that exist on this range are 2 and -1. And so now we're going to assess by a number line which one of these is a max and which one of these is a min. Since I'm going to go ahead and assume that it's going to be the max and a min, going to be a max and a min, and that we're not going to have to concern ourselves with which one's the global, which one's the local. Because since there are 2 points, if you remember with that graphing problem up above, where I had to kind of throw in a minimum there in order to make the criteria fit the graph, or make the graph fit the criteria, excuse me, I had to add this min in here, which again, I'm going to check and make sure that I didn't miswrite this when I was copying it from the book. But in order to go from a maximum to a minimum, there's got to be a change in concavity. And so it's going to be unlikely that there are going to be 2 maxes, because since we did this symbolically, say that there was a max at 1 and a max at 2, we would still be able to crank out symbolically that there is a minimum at this, say that's 1.5. And so since we only have these 2 values, we can kind of assume that one's going to be a max and one's going to be a min. So assessing this by the number line, we're going to first write up the information that we know. So we're drawing a number line of f prime of x. Up here, we were dealing with function values. We did find f prime of x in order to determine what exactly the critical point was. But here, we're going to focus on f prime of x. Rather than plugging into this function, we're going to plug into the derivative. Rather than plugging into the original polynomial function, we're going to plug into the derivative that we've taken to figure out what if these are maxima or min, if this is a max or a min. So in order to do that, I'm going to think, okay, I know that the derivative at -1 and 2, that those are both going to be 0. I don't know which one's a max yet. I don't know which one's a min yet. But I know that in order to have a maximum or a minimum, there has to be a change in the first derivative. So we're going to go, in order to go from negative to positive, we're going to pass 0 by the IBT. In order to have a minimum, we're going to go from decreasing to increasing. Negative first derivative equal to 0, positive first derivative. And then the same sort of thing is going to happen here if we have a max. So this graph is no longer representative of this. These are just this is just me throwing up doodles to talk about changes in the first derivative and how it appears on the graph relative to a max or a min. So again, the function is decreasing, and therefore f prime is less than 0. F prime is negative, and a negative f prime means that the function is decreasing. And if that changes from negative to positive, it's going to have to pass 0, and that means that we have a minimum. And so that's like the graphical representation of what we're going to be thinking about when we try to figure out whether or not it's positive here, negative here, positive here, whatever it is. And so in order to figure out what the sign of the derivative is in between these maxes and mins, because that's what we care about, is how they're changing before and after the extreme points. In order to figure that out, we're just going to plug it into this derivative function. And so the first point, so I'll start by saying you choose easy numbers. You choose numbers that are going to work for you. And more often than not, those are going to be whole numbers. So the numbers that I chose were -2, 0, and 3. If you can use 0, always use 0. It's just going to save you time. And so the first one we're going to start with left to right is f prime of -2. We're going to figure out what f prime of -2 is. So again, we're plugging into this function here. And when we crunch these numbers, we get that f prime of -2 is equal to 24. We don't really care what the actual function value is. If you can look at this and in your head just kind of recognize that one of these that the sums are going to even out such that it's going to be less than or greater than 0, you could say that f prime of you could simplify this and you wouldn't have to necessarily crunch it down to this integer number here. The only reason I would say not to do that on an exam is, say, if you make a mistake, then there's less of a chance that you'll get points back, because then Dr. Zalecki or I wouldn't be able to determine where the mistake was. But still, if you can just determine if it's greater or less than 0, that's the only piece of information that we really care about. We're just going to throw up a positive sign here because we know that it's greater than 0, and we know that the function, the f of x function, is increasing because the f prime of x function is positive. And so we'll do that again for 0. Shakes out to be -12, which is less than 0. And you guys probably could have guessed that based off of my spiel before, talking about how we have to have a change in the first derivative in order for it to cross 0, in order for there to be a max or a min. And so we get that this is negative. Thinking ahead, this is probably going to be positive. This is a simple polynomial, so we're not going to expect any curveballs really. And then when we figure out what that value is, look at that, it's greater than 0. We get positive, negative, positive. And so now we got to think visually, okay, what does this look like? We've got a function. So this, I want to start by saying this number line here is f prime of x. This function here is my doodle of f of x. So we've got a function that's increasing. To the left of -1, f prime is positive, and so f of x is increasing. Here we have f prime of x being equal to 0 at this maximum. Then f of x is decreasing because f prime of x is negative until we reach the point x equal to 2, at which point we change and we have f prime of x being greater than 0, being positive, so f of x is increasing. And you wouldn't be expected to draw this doodle up. An acceptable final answer is just to say global max at x is equal to -1, global min at x is equal to 2. Any questions on this one?
Isn't another way to determine whether it's concave up or down, isn't that how you use the second derivative?
Yes. So we're doing the first derivative test, the concavity test we will use, but since we're just trying to figure out if it's a max or a min, we really only need to concern ourselves with the first derivative.
Okay.
But yep, concavity test will come up. It's a part of the candidates test that I mentioned earlier. The first derivative test is just one part of the candidates test. All right, number 49. So I don't draw up separate number lines. I just do I'll just plug through these values and then I'll show you what my little graph doodle looks like. But I don't handhold quite as much with this problem. So we have f prime of x having taken the derivative using the power rule. Again, we don't, so I wouldn't say that this information here is negligible, but having done the problem, I can tell you that the values that we're given are within this range. And so we don't really have to concern ourselves with it. So first, we're going to factor out a 12x. In general, if you've got we had another problem earlier in recitation today where we had the last term here, it had a variable, and we were able to factor out that variable. If you can, you should. It simplifies the factoring process. You won't be able to factor it without doing that. So we're factoring out a 12x here, which eventually on its own will be set equal to 0 because we can set both of these equal to 0. But in order to figure out what these two extrema are, what these two x values are going to be equal to, we're going to have to factor this. We've already factored this exact phrase, x squared minus x minus 2. And so setting 12x equal to 0, we get that x is equal to 0. Then we get x is equal to 2. And we get x is equal to -1. So these are all our critical points. In the last problem, we only had 2. And we could assume that one was going to be a max and one was going to be a min. Now we're either going to have 2 maxes and 1 min, or the reverse, 2 mins and 1 max, which means we're going to have to determine between those 2 maxes or those 2 mins, which one's a global and which one's a local. And we'll save that step for last. First thing we're going to have to do is determine if they're a max or if they're a min. And so we write in the information that we know. We know that f prime of x is going to be equal to 0 at all 3 of these points. And then the points that I chose to look at, so -2, that one's pretty obvious. 1/2 is going to be the simplest fraction to plug into these to plug into these power functions up here. And it's really not, I don't write out the computation of plugging it in, but it's really not difficult. Then we get +1 and 3. These 3 numbers should be pretty obvious why I chose them. This one also fairly obvious, although it might be a little bit off-putting for someone who doesn't want to deal with fractions. So first, come on, there we go. First derivative we're going to take is f prime of -2. So when we plug that in, we get that it's -96. Again, we don't necessarily care about what the exact integer value is, or if it's not an integer, we don't care what that exact numerical value is. We just care relative, or we just care whether or not it's positive or negative. So we get that it's negative, and we throw a negative sign up there. Next value that we are going to evaluate is f prime of -1/2. So like I said, I don't write out the simplification of this, but 1/2 to the third power, or -1/2 to the third power, is going to be -1/8. So -1 times -1 times -1. We're going to keep that negative sign because we're multiplying by -1 3 times. And then 1 cubed is 1, and 2 cubed is 8. So then it would be 12 times -1/8 for this first term. And then you do it the same for the others. And we get 7.5 as our answer. Again, we only care whether or not it's positive or negative. And we probably could have guessed that it was going to be positive, and we were right. We can probably guess also that this is going to be negative and this is going to be positive, but we're going to cover all of our bases and show that we know how to do this problem, and we're not just assuming based off of patterns that we know what this is. We get that f of 1 is negative, like we expected, and we get that f of 3 is positive, like we expected. And so now you could just write there is an, well, actually, no, you can do that. I'll take that back. So we'll move on to the next part here, which is conceptualizing where is a min, where is a max. If looking at these negative and positive signs doesn't register in your brain as which one of these should be a maximum, which one of these should be a minimum, then I recommend doing a little doodle. So we've got a function that's decreasing and then increasing and then decreasing and then increasing. So that means we've got 2 mins and a max. Off the bat, we can just say that there's an absolute or a global maximum at x is equal to 0. There's no other competition. It's the only maximum, first of all, within the range -infinity to infinity. But within this specific problem, it's the only maximum within -2 to 3. And I say that bit about -infinity to infinity because that's the domain of polynomial functions. But this problem specifies -2 to 3. And so now we have to determine which of these mins has the least function value, which is the smallest. So in order to do that, we're going to do what we did with this first problem here, and we're just going to assess by relative function values. Well, not exactly the same thing. We're just going to find the function value of f of 2, -2, excuse me, and find the function value. We're going to find the function value of f of -1, and we're going to find the function value of f of 2, and we're going to see which one is less. So f of -1 shakes out to be -4. F of 2 is -31. And so then our absolute minimum is at x is equal to 2. That is the last of this type of problem that we're going to do. Any questions before we move on to section 3.2? Okay. All right. Verify that the function satisfies the mean value theorem. Find all C that satisfy. So we've talked about the IVT before. I mentioned it earlier today when I was talking about an earlier problem. So the intermediate value theorem, basically, the way that we care about it within the context of the problems that have been presented today is that if you're going from a negative derivative to a positive derivative, at some point the derivative has to be equal to 0. That intermediate value, that's what we care about for the IVT. The mean value theorem, when we're taking a mean, we're taking an estimation, we want to find the C value at which the derivative is equal to the estimate, the mean derivative, over a given range. So if that doesn't make sense, I will make sure that it does as we go through. And we also want to satisfy the criteria of the MVT. So the criteria for the MVT is that f of x must be continuous, close bracket, on a to b, and differentiable on a to b. This looks familiar to, so when we talked about differentiability and what makes a function differentiable and not differentiable, we said that you couldn't differentiate a sharp point, you couldn't differentiate an endpoint, can't differentiate holes, things like that. You need to know what the next value in the sequence is, and it needs to follow that same general trend in order to figure out what in order to call it differentiable. And so that's why we do closed brackets, because we can't differentiate an endpoint. We need it to be continuous on a to b. If we're going to talk about the function value a, we need to make sure that that's not a hole. We need to make sure that that's included in the range of values that we're talking about. So when they talk about, when they ask us to verify that the function satisfies the MVT, you want to say, yes, it is continuous on closed bracket a to b. Yes, it is differentiable on open bracket a to b. So this is the criteria bit here. This is sort of a breakdown of how you do these problems. So we're going to find an estimate. What is the derivative on open bracket a to b? Because we can't take the derivative of endpoints. And so once we find what that estimate is, and with simple functions, more often than not, the estimate is going to be equal to the actual value that we're looking for. I shouldn't say the actual value that we're looking for, because the actual value that we're looking for is the C value that corresponds to the derivative. So if we say that f prime, if we find the slope estimate, let's call it Z, and we say that f prime of x on the range A to B is equal to Z, we then want to find the x value equal to C. We're going to call it C. So we want to find f prime of C when f prime is equal to Z. So find the C that corresponds to the slope. I know I'm just saying, it might sound a little bit like mumbo jumbo. Once we assign some symbols to this, hopefully it'll make a little bit more sense. So we are given our range here, A to B. This is a case where the range is particularly important in how we're going to take care of this problem. Up here, it may or may not have influenced how we're going to go about solving the problem. Here, it is integral to how we're going to finish this problem. So first, we're going to take the derivative. Well, first, we're going to verify that the function satisfies the MBT. Polynomials are easy. They are continuous on negative infinity to infinity. As long as there's nothing in the denominator, there's nothing that's going to cause this to be discontinuous. And we know that they're differentiable from negative infinity to positive infinity. So since f of x is a polynomial, it satisfies the criteria for the MBT. Next thing we're going to do is we are going to take, I keep wanting to say that we're going to take the derivative. We are going to take the derivative, and I'll come back to that step in a second here, just because we haven't introduced this. So f prime of C, this is going to be your go-to equation for when you're doing MBT, and I rewrite it later in the last problem. So if it's a little sloppy, I apologize, but it's not the end of the world. So it's going to be f of B minus f of A. So we want to find, I know it's a little funky because alphabetically C comes after A and B, but we want to find some value C that is between A and B such that the derivative of the derivative at C is equal to the estimation of the derivative from A to B. So this looks like that change in y over change in x formula. It's y2 minus y1 over x2 minus x1. And so what we want to do is we're going to estimate this, and then we're going to find the C value that corresponds. So we're going to go about it as, so we're first going to find what f of B and f of A are. So f of B in this case is f of A in this case is f of 0. So we just plug in and we get that it's equal to 1. F of B in this case is 2. And that is equal to positive 3. And so now we're going to plug in those function values. And we get that our derivative estimate is equal to 1. Since this is such a simple number and a simple function, this ends up being an accurate representation. But I just want to remind you guys that this formula here does not always give you the exact derivative. It is an estimation. But when you're dealing with a simple polynomial, more often than not, you will get an accurate estimation. So what I've done here, now that I've figured out exactly what the derivative is, well, not exactly, I figured out the estimate of the derivative over this range, A to B, I'm going to have to figure out what that x value is. What do I know about f prime of C or f prime of x? I can figure out what f prime of x is since I'm given the original function. And so that's what I did here. I took the derivative by dropping 2 and then dropping the x, negative 3. So I get the derivative is equal to 4x minus 3. 4x minus 3 is equal to 1. We want to find the C value at which that is the exact derivative. And so f prime of C is equal to 1, which is equal to 4c minus 3. I'm looking for the specific value, and so I'm plugging in C for where there should be x's, or where we're used to seeing x's. And now we're going to isolate our terms, and we get that 4c is equal to 4, or C is equal to 1. And then we have answered the question, find all C that satisfy. I didn't write out the full question, but the rest of the question didn't give any more context, in my opinion. But if you want to see specifically what an MVT problem, what the question itself would look like, go ahead and look at section 3.2. There's a whole bunch of examples that you can look at. The MVT will absolutely be on your exam. The MVT will come up on your final exam as well. And so will the IVT. And so it is helpful. So IVT you won't see on this upcoming exam. I would not expect you to see on the upcoming exam. But when it comes time for the final, I would definitely do a compare and contrast between these two, just so that you've got them straight in your head, because there will be at least one of each on your final exam. Any questions on going about MBT problems before I move on to another example? Okay. F of x is equal to the cubed root of x on the range, close bracket, 0 to 1. So we know for the MBT, we are going to have to find what f of 0 and f of 1 are in order to estimate f of 1 minus f of 0 over 1 minus 0, which is equal to f prime of x. So first we're going to verify that it checks out with the criteria. So I'll come back to what I was saying in just a second. It is, I think it's worth it to point out why this is continuous and why it's differentiable. So I make a little note here. There's no opportunity for a whole. There's nothing in the denominator. And there are no possible irrational function values that are going to come out of this cube root of x, specifically on 0 to 1. So if this was negative 1 to 1, then the MBT would not apply. Well, we'll say negative 2 to 1, because you can't take the cube root of negative 2. So if the range were a little bit different here, then maybe the MBT would not apply. But we know that if we plug in 0 or if we plug in 1, we're going to get a rational number. And there's no whole or anything funky like that that would lead us to believe that it would be discontinuous. And so we can say that it satisfies the criteria of the MBT. So now we're going to find out what those function values are. Fairly easy. We plug in 0, we plug in 1. And so now we'll plug in these function values into this equation that we're going to use for all MBT. We get that the derivative is equal to 1. So now in order to figure out what C value specifically satisfies what this, so like I said, we're finding the estimate of a function. So I believe, if I remember correctly, the visual representation for finding the MBT is that on the range A to B, this is the estimate. This is what we're finding by using this estimation technique here. We're finding a secant line from A to B, but that's clearly an estimation. What we want to find is, and maybe C's right here, we don't know. We want to find a tangent line that is parallel to this secant line. That's what's happening. That's what we're doing by finding the C value. We're finding the exact point on the function that has this derivative. We found this derivative by estimating across this whole function by taking a secant value. Now we want to find the C value that corresponds to the specific tangent line value. So we're going to take the derivative of this. F of x is actually equal to x to the 1/3. I didn't write that down. But when we take the derivative, we get 1/3 x to the negative 2/3. And so we want to find C. So f prime of C is equal to 1, which is equal to 1/3 C to the negative 2/3. So now we've got to isolate this C. We've got to work with this 1 and this 1/3 C to the negative 2/3 in order to figure out what C is specifically. Find the x value at which the derivative is 1. And so first thing I do is multiply by 3 on both sides. Now what I do is I put this to the negative 3/2 to cancel out this power to just get it to be C to the first, which means I have to put this 3 to the negative 3/2. So I get that C is equal to the negative 3/2. The negative 3/2 is going to cancel. So the reason I did negative 3/2 because I want to find what C is. I want to find what C to the first is. And so what times negative 2/3 is going to give me positive 1? Negative 3/2. And so then when we do a power manipulation, there's no way to come up with a more simplified answer than this. The only other answer you could give really is a decimal answer, which obviously you would not be expected to do on an exam. But you can't take the square root of 3. We've got to cube it. And then, so again, this negative sign is going to pop the number into the denominator. 3 cubed is 27. We can't take the square root of 3, and we can't take the square root of 27, and so we maintain that square root symbol in the denominator. And the derivative of f of x is equal to 1 at C, which is equal to 1 over the square root of 27. Any questions? Let's see. I will look at that later because it looks like some of those are private. All right. Does there exist a function such that f of 0 is equal to -1, f of 2 is equal to 4, and f prime of x is less than or equal to 2 for all values of x? So I want to talk about how you would determine what this problem is asking you to do. And I don't know that I have the most direct answer for you, but I'm going to talk about the way that I kind of go through it in my head, or I did when I was taking this class. And first thing I want to say is, within the context of this upcoming exam, if you see a question like this that is like, does there exist something? Unless it's a true or false, we haven't seen any of those types of problems thus far in this class. We've been asked, is it possible for a function to exist with this criteria? Is it possible for the derivative to be this if the function is this or that? We've seen true or false problems like that in the past. But these general and open-ended questions, we don't see them very often. And so the next step in my mind was, okay, if I'm not going to be using my classic computational skills, if I'm not going to be taking a derivative, if I'm not going to be integrating, which we haven't gotten to yet, if I'm not going to be doing something that I'm maybe a little bit more comfortable with, maybe I'm going to be applying a theorem. And so then what possible theorems can I use? IVT isn't going to help you in this case. But we know that for the MVT, we need two function values in order to plug it into that f prime of c is equal to f of b minus f of a over b minus a. And then that will give us what the derivative is. And so since this is a does there exist problem, we have two options, either to prove it or to disprove it. And in order to prove it, we could sit around all day trying to come up with a specific example that works that may not exist. We could sit around and try to come up with however many variations of polynomials or whatever to try and come up with a function that fits this criteria, or we can use a theorem that will disprove it. And the theorem in this case that we have, because we really don't introduce a lot of theorems to you in this class, the IVT and the MVT are the two big ones that we have introduced to you so far. And so we're going to use the MVT to first try and disprove it. So what that looks like is we're going to start with this equation here, just like I mentioned before. We'll plug in those function values and x values. And now this is where the proving or disproving part comes in. If this answer here, and we'll plug in the function values first, but if this answer here is 2 or greater, then we have come up with an example that does satisfy the criteria. And then the answer would be yes, there exists a function. Doesn't have to be true for all functions. But if this here is, if this f prime of c value is greater than 2 or equal to 2, then we have answered the question affirmatively because we've come up with one example that satisfies these criteria. But when we plug in, we get an answer that is 5 halves, which is less. Yeah, no, 2.5, which is greater. Oh, I'm sorry, I misspoke before. So we need the derivative to be less than or equal to 2. The derivative in this case is 2.5. It is greater than 2. So if we had come up with an example that was, say, 1.5 or 2 or 1, then we would have proved this true. There does exist a function that satisfies all these criteria for all x. But since we found the function or the derivative at c, and we're not even going to concern ourselves with what c is, but since we found the function value at c, which is a part of all x, not the function value, the derivative at c, and c being a part of all x, is greater than 2, this cannot be true. We've just broken one of the criteria, and so the question is answered no, there does not exist a function. Since 5 halves is greater than 2 for some value c, and we don't care specifically what c is in this case, this problem up here asked us to find all c that satisfy. This is going to be the most common application of the MVT. It's going to be a problem like this, find the c. But for this one, since 5 halves is greater than 2 for some c value, and we can just say some c value because part of the criteria is that it has to be for all x values. All we have to do is find one c value, one x value that disproves that. So there does not exist a function that satisfies the given criteria. And that would be all you need to do for a problem like this. This part here, obviously, you wouldn't need to include. You just have to find, so a problem like this, if you were given this specific problem, but with different numbers on the exam, it would be set up so that it would work out for you to disprove it. The answer would more likely than not, they wouldn't be expecting you to prove it, because we haven't given you the means to prove that. And also this problem, since this problem is written because we want you to apply the MBT, we want you to disprove the criteria. And so there is going to be a break. There's going to be something that doesn't quite match up or line up in the criteria. And so, like I said, if you were doing a true or false, you would think, okay, I can either come up with an example that proves it, or I can disprove it. For a problem like this, you're going to be disproving it every time, because that's how we're going to get you to apply the MBT. That's how we're going to we're going to have you show us that you understand the MBT and how to apply it in this case. Any questions on this one? Okay. So at this point, we are all set for the day. That's all that I've got for us. Oh, it looks like I went a little bit over it. I apologize about that. But I will hang around for a second and I will look at those messages that I didn't answer from before.
Thank you.
Yep,
Thank you.
no problem. Jaffrey, or Unser, I don't know why I just called you by your last name. So I hope that your questions have been answered at this point. MBT is the mean value theorem, which I just went over quite a few times. Difference between global and local. A global is the absolute, the greatest. A local is, so, well, do you understand at this point the difference between a global?
Yeah, most
Okay.
of my questions were answered from the
Okay.
initial questions, but when's the next exam?
You're gonna have to check the syllabus for that one. I don't know.
All right.
But in general, if you send me messages in the chat, expect me to answer them at the end of recitation. If you want me to answer something in real time, speak up and say so, because I typically, especially if someone's sending me a private message that doesn't have to do with recitation, I don't want my screencast to show up for everybody.
Yep.
So if you got a question, just say so out loud, unless you're okay with me waiting till the end of recitation.
Got it. Thank you.
Okay,
No problem. Have a
Thank
good one.
you.
no problem. Tristan, are you, or I meant to say, Keenan, are you still here?
Yep, right here.
So do you understand?
What's the test, the candidates test?
Okay, so the candidates test, we'll talk about, so candidates test, oh my gosh, it's been so long. Basically, the candidates test is nothing different than what I've already introduced to you today. It's just kind of this blanket term that wraps in using the first derivative test and the second derivative test, or the concavity test. Since the problems we've asked you so far haven't really been concerning concavity, we don't have to worry about the candidates test yet. Dr. Zalecki may or may not even call it the candidates test. That's just what I was taught it as in high school, because we're talking about maxes and mins, and then we need to figure out if they're concave up, concave down, whatever. And so we have all of these critical points, and those are our candidates for extrema. And so that's why it's called the candidates test. And when we get into a little bit more complicated graphing, we're going to need to use concavity, the second derivative. We're going to have to use a number line for that in order to answer our questions. And so the candidates test is the blanket term using both the first and the second derivative tests in order to answer problems that we have not yet taught you. That make sense?
Mm-hmm.
Cool.
Alrighty. So the MVTs is basically to find like the different points, the different critical numbers. So, and then I forgot what the IVT was. That's to find what again?
So I wouldn't say that. So the intermediate value theorem. So my go-to representation of this is, say that you are driving and you start at 0 and then you get up to 25 miles an hour. At some point you had to have hit 10 miles per hour. And that is what is asserted by the intermediate value theorem. If we know that at some point our, so in this case it would be velocity, or if position is x of t, then it would be x prime of t, or v of t. If we know that velocity or our speed at one point was equal to 0, and then we know at some point x prime of t is going to be equal to 25, there has to exist a t value. There must be a point in time at which your velocity was 10. If you went from 0 to 25, you had to have hit 10 at some point. So what's that t value? The way that that's different from the MVT is that we're not going from 0 to 25. We're not, so intermediate value versus mean value theorem. By saying intermediate, we're talking about crossing, we're crossing those values. That's why I say if we go from 0 to 25, we had to hit 10. When we're talking about the mean value theorem, taking a mean is an estimation technique. That's the way you can remember. So if you remember that doodle that I put up where I was talking about secant lines and I connected the two ends of the graph and I said, this is the estimate of the derivative. We need to find the specific function value or the specific x value that corresponds to, that has that derivative. So we just found an estimate, and by the mean value theorem, there must be a function value that has the derivative equal to the estimate. That's what the mean value theorem is. And so we're going to find that c value that corresponds to the f prime of c being equal to the estimate, which is why we say f prime of c is equal to f of b minus f of a over b minus a. So the actual derivative is equal to the estimate derivative. What's that c of the actual derivative? What's that c in f prime of c?
So one's basically like, what's this point, and one's like, what's the slope kind of thing.
Yeah, that's one way you could think about it. Yeah.
All
It's
right,
a
that makes sense.
simplification, but yeah, in terms of like keeping them separate in your brain, that's definitely a way to think about it.
That makes sense. Thank you.
Yeah, no problem.
Have a nice day.
Yeah, you too.